Hi everyone, and welcome to today's webinar together with Onshape and SimScale. My name is David. Here with me is Joe from Onshape, and we'll have the pleasure to host you for the next, 30 minutes, Joe, I suppose, and we'll talk about end-to-end design optimization in that session. And in fact, what you see on the screen here will be the design and simulation example that we're going to use for the next 30 minutes. And we'll start with an introduction. Joe, do you want to take over?
Yeah, I am Joe Dunn. I'm with Onshape. My role at Onshape is the technical partnerships, and I've been working with David for quite a while with SimScale. What have we been doing? 5 years now, maybe?
Ish,
yeah. Ish, yeah, ish is a good word. So we'll talk about Onshape in a second. So I think, hi.
And I'm David, again, co-founder and CEO of SimScale. I did more application engineering work in the early days, but I'm still, can run a simulation here and there. So I'm happy to sort of talk about electronics cooling analysis today, conjugate heat transfer. So excited about this. Without further ado, we'll start with a quick introduction of the two companies. I'm not sure, there's some people in the audience that already know SimScale. For the ones that don't, we're an 80-ish people company, founded out of Munich, Germany, have meanwhile offices also at the East Coast. Can support our customers across 6 time zones. And what we do is SimScale.com is an engineering simulation platform in the cloud, meaning, and you'll see it later, for example, analysis such as this little image shows a transient wind loading analysis on a building, but also today we're going to talk about thermal management analysis. So it's an end-to-end simulation environment, general purpose physics, so structural analysis, thermal analysis, over all the way to CFD, and that end-to-end in a web browser. And I don't want to talk too much about it because we're going to see it in action anyways, so I'll hand over to you, Joe.
Okay, thanks, David. So we'll go through just some basic. I'm going to assume many of you have not heard of Onshape before. So what we are is we are a new engineering platform, and really the key to Onshape is real-time development. Dave, you can just kind of go to the next slide.
Oh, of course. Yeah. Sorry, I'm not the best video jockey.
You're the monkey. You're the monkey. Yeah. And we've been learning a lot. We've been available, and people are adopting Onshape at an accelerating rate. And actually, I would be willing to bet, regardless of what industry you're in, if you haven't moved to Onshape yet, your competitors have. And it's really compelling and a very different world than in the past. And we were the team that developed SolidWorks. I was with SolidWorks for 20 years, and our developers and our team literally are the ones that developed and wrote the code for SolidWorks. And we felt that there was a time to start from scratch and build a tool that really solves some of the problems that the existing desktop CAD systems just don't, right? There are really, really a lot of ways for you to get a better return on your investment, get your products built faster, be more efficient. And, the things that we see as a supply chain, highly customized products, these are all common things I'm sure that you're going to recognize in very generic terms. But in each of these areas, you're going to get a huge benefit with Onshape. You can go to the next slide, David. Just very briefly, you've got IT, where the idea of your company having to be an IT manager for CAD is just kind of not a very productive thing. I don't care if you have one computer or if you have thousands of users. With a platform like Onshape, platform like SimScale, that goes away. Okay, those are things you just shouldn't be. You should be spending your time on engineering, not on being an IT guy. And if you have a very rigid control process, if you're stuck in a process where typically people have, because they're file-based, someone has to check a file out, they check it in, only one person can work on a time, and it's a very serial process, and we've completely changed that paradigm in the workflow. So it really just creates more iterations, more projects, more and better design. And, I mentioned this, it's a file-based approach is what we built with SolidWorks, and it's a great tool. I think most people probably are relatively happy with SolidWorks or whatever system you're using. The thing is that you're going to be behind if you haven't started to move, because that is a process that's slower, more prone to error, very much harder to collaborate with people, and if your competitors are using Onshape, you're already behind is really what we're seeing, and people are seeing the productivities in real time at this point. Yeah, we have transitions, so. But for sure, it kind of goes back to the, serial process, managing files, managing file systems, worrying about what servers you're on, worrying about what operating system, what computer you have, what software version you have, did you install the service packs, does it crash, does it work? I mean, these are things that are gone, and they're no longer, your company shouldn't be spending time doing that. And you should be spending time on the innovation side and really concentrating on just doing what your company does, designing better products. I just want to really briefly go through what our product is in general, because those are kind of generic benefits. But we are a CAD system. We're a mechanical CAD system. It's a high-end production level tool. That means we do everything that you do with whatever. I don't care what tool you're using, whether it's CATIA, SolidWorks, or one of the above. There's 10 different products out there that people use. This is for industrial strength, high-end, difficult modeling, large assembly design products. And every bit of our product, I could spend 2 hours just on the CAD side of how we've improved over the existing CAD systems. Where the product starts to, and sorry, we're getting a little clip on that, that's my fault on the image, but where the benefits start to really become obvious is where you have a process where people check in and check out and work in a serial manner, right? The idea, or a bill of materials that you can't edit, or going through release management where you have some process that's just cumbersome and you don't like to use. We've really taken a look and said, how can we change this dynamic? You can't do it with the existing systems. If you're moving files around, if you have a file, one person can work on that file at a time. That one file has so many limitations. Just if I was to cover configurations for those of you that use SolidWorks. Configurations are powerful. You can't do revision management per configuration. You can't let two people edit different configurations at the same time. You can't control them the way you want. You certainly can't have an infinite number of configurations. I mean, and I could go on and on. And release management is just transparently part of Onshape. That means you don't have to install a vault. You don't have to install a separate piece of software. And every piece of Onshape understands what a version is, what a configuration is, what a revision is. A drawing can refer to a specific revision of a specific configuration. Same with the assemblies. It's a gated process where you have complete control and you're not getting that trickle down or that cascading effect that we used to have with products like SolidWorks, where a change would ripple through everything. Made everything would start breaking. You really couldn't tell what's going on, and you had nothing but errors in your assembly and everything. Just to make a simple change, we really made this a controlled but a simultaneous process. Definitely something that is unique to Onshape. Everything is that I've talked about, hopefully, but the idea of multiple people actually working on the same thing in a collaborative environment. You'll see David and I, we could work together in this, and we're going to show a sample project, and he and I can work in the project. He can be doing his CFD studies. He can be making modifications to the design for his purposes while I work on the same thing. Our DNA is built with collaboration in mind, with no extra effort. We simply work together on the same project, whether it's the same assembly or it could be the same part. For that matter, it can be the same sketch. Not that that's a great idea, but it works. Our product is built from the ground up with collaboration. And you'll see some examples of that in a minute. Of course, just some basics. One of the things about the cloud that comes up sometimes is people say, all right, well, what about my security? And the thing is that, whether it's needing a full audit trail, whether it's compliancy through different standards out there, the cloud actually is the most secure way to secure it, to manage your data, to make sure that you don't have unauthorized access, to make sure that there aren't phishing events that can impact your data. It is the best way to protect your intellectual property. And we've gone through an inordinate amount of, I can't talk, but we really, really concentrate on security, privacy, and making sure that this is the absolute best way to secure your data and to make sure that you have complete insight and control over it. And the other thing that's really interesting is that, Onshape is a database, okay? I keep saying there's no files, it's a database. But what does that mean? That means when you log in, that means when everybody's using your system, you can also really get a a God's eye view of what's going on. You know who's done what, where, who's accessed things, what things have been done. A full audit trail is built into Onshape. And this becomes handy when you want to really start to not only control your data and make sure that it's protected, but to really gain insights to projects, people, locations. I mean, we have so many different ways for you to look at your data and to make decisions based off that data. That back to you, David. That was my.
I was at this point where I could anticipate the slide switches, so you shouldn't have said it anymore. Anyways, and I guess that's where we're, that's SimScale and Onshape. And what Joe and me want to do today is not, focus on I don't know, the details of parametric modeling in Onshape, or the details of turbulence modeling in SimScale, but rather show how these new generations of tools allow for sophisticated design workflows, completely cloud-based, completely in a web browser, right? And as an example, we're going to use this medical equipment device, sort of a heater, programmable heater, where we have, of course, you can see it already, sheet metal and normal model, solid modeling inside Onshape that Joe will show. And because of this piece of equipment, having to deal with thermal management, we have a PCB. It's hard to see. We're going to see it in a second. We have a bunch of electronics components and a board in here, and those heated up baskets that we have to, maintain the heat. We have to manage the heat, and that's what we're going to do in SimScale. And then to sort of cap it off is we're going to show how these tools then allow to design one configuration in Onshape, quickly check its performance. In this case, it's thermal performance in SimScale, to then go quickly back and do iterative design and go to a more optimal performance of your design. That's what we're going to show. We try to keep this brief. Joe, we really try, right? And yeah, let's do it. Joe, I guess that's where we'll hop over to your screen. Is that right?
Okay. Yeah, sure.
Change presenter.
Okay. So I want to just walk through some basics of Onshape, just the general concept here. I've logged into my corporate account. It's called, in this case, we have a little logo up here. It's called Cyberdyne Systems, and I have lots of projects. One of the nice things about Onshape is I don't care what operating system, what computer I'm on. I can navigate visually. I can navigate by labels. I can navigate by folders or projects. We have tons of organizational tools. But ultimately, when you pick something, whether it's a project or whether it's in a folder or whether it's with Teams, I have instant access to all of my data and all of my project information. And this is the heating mantle that David was just describing. And we can visually inspect it. We can do all kinds of different things to we have parts, assemblies, and drawings just like you would expect. If I click on some of these tabs at the bottom, we call these elements, where this is breaking out different pieces of the design. In this case, these are all my sheet metal parts, okay? And I can show the flat, I can show the bend tables, I can show all kinds of information about it. I can visually browse through all of these things. And it's going to be a workflow very similar to anybody that uses a professional feature-based parametric modeler. That's exactly what we've embraced. And I can turn some parts off. You can see transparently there's a PC board in there. We have some sheet metal. We have all kinds of things. But this is the model that, let's just say for the sake of argument, this is the project that the design engineer built. Let's call me the design engineer. David's going to be the analysis expert who's going to make sure that the thing actually works. It's great that I design it, but he's going to make sure that it's functional. And what we can do, though, is something unique in Onshape is something called branching, and something that is new to the CAD world anyway. And this idea of branching and showing different design iterations is that I can navigate through. You can see I have all these different branches, and the only way to do something like what you're seeing here with any system I'm aware of in the CAD world, in the mechanical CAD world, you would be making file copies and a lot of copies, because you'd have to copy every file, every part, every assembly, every drawing, and you just have a huge mess just to do what we're doing here. And what I can do is click on these and visually inspect them to say, okay, we see that my design team, my CFD team has come up with a design iteration already where they've they've simplified things. You can see that they have a volume that they've calculated that I think David's going to get into more. They've got simplified interfaces for the flow in the inlets and outlets. Things like the PC board. You notice that it's a simplified block representation versus all that detail that you saw earlier. By the way, all this is automatic. This is something that we do automatically to simplify the board. So it's some very interesting capabilities of Onshape. But what I really want to show is the value of having these branches, because here's another iteration that's done, and there's some design changes, and visually you might be able to spot them right away. And if I click on design, that's design change 1, design change 2. You know, it's very simple to navigate. And it's one thing to visually inspect these to say, okay, all right, I can obviously see what the differences are, but we do a lot better than that. So one thing I can do is say, you know, I want to just do a compare between those two branches, because what actually changed? So instead of us going through, and let me go to the sheet metal part, that's always a good one to compare. And what we've done is we've tried to give a very comprehensive overview of presenting the data of, okay, between these two branches, what did each individual or multiple users do to make those changes? And we'll let this thing it's going to go through, and it's evaluating all the different elements, and it's doing a compare between all the different branches and or those two branches and the elements, and we'll be able to use a slider in a second and kind of just visually see, and it's showing in red, the difference between change 2 and change 1. And I can turn parts on and off, and I can show some other ways of doing this, but it starts to give us a very good overview of not only visually what's changed. We can see semantically, these are showing these two faces have had some changes. These are not equal. This sketch has some differences. So I could spend another 15, 20 minutes just on what you're seeing here, but suffice to say that we really try to give you a very clear and precise indication of, with those different branches, what has changed between them. If I go back over here, oops. Let's go back to the main. David, I think what we probably should do is let's just go into the analysis part and talk about how we can go and take this and start doing some let's see if this one's going to work.
Sounds good.
Yep.
Great. So Joe already showed the baseline design, and he started already showing what types of design iterations we're going to do to improve the performance. And so how these design changes were identified, let's take a look at that, right? Because that's what we use SimScale for. Here, just quickly, to not make this sort of a canned demo, what was done, you've seen it already, right, is that from the original design that had all geometric detail on the electronics board, we used a specific feature script inside Onshape that allowed us to automatically remove the detail of that electronics board, which comes in quite nicely and is helpful for the CFD part of that. And so now the thermal management challenge that we're trying to manage here is that the heating baskets, both of them have about 12.5 watts heating loss, right? So that, of course, is supposed to go into whatever I put in here that I actually want to heat up, but also it'll go inside the enclosure, right, where I do not want to have that heat. On the electronics for the logic, and we have about 4 watts of a wattage of 4 watts, transformers, coils, capacitors. So overall, we're looking at 28-ish wattage inside a 20 times 20 centimeter enclosure. So it's not crazy. I wouldn't call it high power, but it's significant, right? So it needs to be managed, and hence passive cooling, by the way, that we could also check quickly, if you could cool this completely passively, doesn't work. So we do have to actively cool that, in this case with 2 fans, right? That's essentially the first approach to this, the first design strategy to get this heat out. We're not going into the details of, there's various materials on here. We have various materials from silicon, copper on the electronics components over to steel, the enclosure, yada, yada, yada. So we'll not go into that. And that's like everything you're seeing here was still done in Onshape. And then the next step to analyze the resulting temperatures on each of those components, because that's what we care about, right? That the semiconductors don't fail, the electronic components don't fail. that was done in SimScale. And so for that, I'll bring up SimScale itself. Let's see if that works. That worked, I suppose, right? Joe, can you see SimScale?
Yep.
Good. So this is now, let's quickly start at the beginning. How this works is, I'll not show that direct import, is that this is now a simple Google Chrome browser as used, as Joe used it, and I can upload a CAD model from a local CAD system I'm using. I can then directly import from Onshape via this button here. Right? That opens a window. I'm not going to go in there because, frankly, that's not my computer and I don't have the password stored, Joe. So next time I'll do that better. But the beauty is that SimScale and Onshape both use the exact same CAD kernel, meaning we can translate data or we can exchange data lossless, right? Of course, in SimScale, we do not have the parametric feature tree, etc., so we don't recover all the logic Onshape has, but do not have any translation problems, which makes the work quite conveniently.
And by the way, the cool thing here is that just to keep this in mind, David's in Germany, I'm in San Diego. We're both working on the exact same representation at the same time. We're probably even on two different types of computers. I don't know if you're on PC or Mac, but this is just a collaborative environment, no matter where you are and what system you're on. So I just wanted to point that out.
Right. And so just without making this, a long tutorial of, how to use SimScale and sort of explain all the details of that simulation setup, just like a 30 seconds walkthrough, right? So we brought in the design, and essentially what you're doing is you're starting off with defining physics, right? What type of analysis are you actually running? Do you, would we want to do a drop test, an FEA drop test of that model, or would you, want to look at, I don't know, all sorts of things. In this case, we're looking at a thermal analysis of this model, and we do want to look at not just conductive heat transfer, meaning how the parts emit their heat and then sort of how it travels through other parts. No, we do, because convective cooling is important in that model, we do need to model the airflow in here as well, right? Hence, we're going to run a conjugate heat transfer analysis in which we're going to look at convection and conduction. In this case, we turned off radiation. We could also model it with radiation. In this case, we disregarded that. The first thing SimScale will do is it'll contact all thermal interfaces between all parts. I'm not going to go into the flow volume extraction because that's a whole, so we extracted a flow volume automatically, yada, yada, yada. But I think Joe covered that already. We assign materials. And so just to get a feeling for the physics, we do have the set power sources we discussed before, right? So we have a component down here that has 1.5 watts, as we've seen on the slide. We have another component with 1 watt, and then another component with 1 watt. That's the 3.5 watts on the electronics board. Then we have up here, each of the baskets, 12.5, right, as we've seen. And then we're bringing in on both sides of the cooling fans heat at 20 degrees Celsius, with 0.3 meters per second. You could also model fan curves or have that rotating, etc. But in this case, we for the sake of this demo, it's a simple inlet condition. Lastly, and then enough physics, we do have an open outlet over here. So we have these vanes in the sheet metal model in Onshape, and that's sort of now how we set up the entire analysis. And I guess where we now are in the design process is we have an initial strategy of how to remove this heat, of how to design the thermal management of this assembly, and now SimScale allows us to actually validate whether or not this makes sense, right? Whether or not this will actually work. And so this analysis is pre-run. I think we're looking at 4 million cells, something like that. So that took about 90 minutes ish to compute. And now we're going to look at results. All right, let's start first with just the, so you can see I saved this state, right? So I actually could now show all, like, you have all parts, you have the air, etc. You have everything that was simulated. You can, slice and dice and, take a look at surface temperatures, yada, yada, yada. In this case, this is now a surface plot of temperature, right? 330 Kelvin, right, is about 50 degrees Celsius. So we can see already, okay, that's going to be a problem, right? A component, an electronics component that goes north of 50 degrees Celsius. In this case, we're considering, you know, that's a limit. We're going to look at quantitative results in a second, and I can, you know, probe all of these points, 3 to 7, right over here, etc. So I can interact with that. But the important information here is that, okay, my baskets are actually okay, right? But I have a problem with my electronics components here. They are too hot. They'll likely fail, melt, whatever. So that's not good. And so before we look at design changes now. What's great now is that you can interrogate essentially the simulation results and try to find sort of, you know, what's wrong here, right? Or where's the potential for improvement? And I have a few slides for that, but just let's do this real quick live here, right? For that, I put a cut section through the air that's inside this enclosure, right? So we're looking now at a cut section, what is that, like a centimeter above the lower face, and we can see already. I mean, that's not the best view. Let's go a bit up, and that's now, like, again, stressing the point. We're looking at a couple of million cells that were simulated here. So that's quite a heavy data set that we're looking at here. But I do not need any local strong machine because this is being rendered on GPU instances in the cloud. So we do have, you know, heavy lifting or heavy compute power server side in the cloud, and we're just, you know, having a lightweight client on our end. And that gets already sort of one thing that gets obvious here, right, is that we have a problem here with airflow coming through here. That's the velocity, right? The red part is 0.35. The blue part is essentially no air moving, right? And we can see that the air is not going sufficiently well around that corner and not hitting enough this component over here, right? I don't want to overdo it. There's more, if we would add more slices, we would also see that the baskets aren't great or aren't well cooled above this this sheet metal part here, right? So that's why we tested cutouts here. We're going to see that in a second. But what I want to get across is that we can really now interrogate how the temperature is distributed, how airflow is going through that enclosure in order to inform our design process, right? To not just, you know, trial and error and test something else, but rather understand what's happening and apply that knowledge to a second design iteration. And the usual things are now in here, right? So we could look at, you know, everybody likes to look at streamlines, etc., so to get a qualitative view of that field, etc. So I don't want to overdo it. We could now animate that, etc. But I think the important information we already got, right? That one issue is certainly this, the orientation in this corner. And another issue, if we would have probed more, are the veins back here. So we're going to change them as well. And that being said, Joe, give me 2 more minutes here, quickly probing back, right? Quickly hopping back to the slide. So that's what we just analyzed, right? So we can see coils and capacitors on the electronic design aren't sufficient. The transformer will work, so that's below limit, but the baskets are also at a level where we do not want to have them, at least not at a junction temperature towards the inside enclosure. And here's a bit of more post-processing, right? We can see that there's a bunch of narrow passages that aren't great for the airflow. So we can really slice and dice and understand how we should guide the air towards efficient cooling. And essentially, that's what we've done, right? We made one design iteration over here on the left. You can see those cutouts. Joe, I'm not sure if it makes sense to hop back to Onshape to show how we've done that. I think you showed the different.
Well, yeah, we were just showing that. I think we could stay here. We were just showing that in the. I did this is reflecting the gray and red area with the compare, so you can see the 2 different design studies. Yeah. Exactly.
And the idea,
more visual.
Yeah, the idea here was because we saw that airflow is sufficiently, or there's a lot of air moving through under that sheet metal part, but not enough over there, right? And so to even that out, you know, we did test these cutouts. And a second change was, instead of actually redesigning the board and, you know, thinking about board placements, just reorienting the board, right? So, you know, no harm done. That doesn't change cost. That doesn't change the fans. That doesn't change anything. Oh no, wait, I don't want to. It was a spoiler now, but I think I assume you know where this is going, right? And you can see now in that SimScale project, I have those 3 different designs brought in from Onshape. And so I don't want to, let's not talk about the design 1, but just quickly about the design 2. Design 1 was the one with the cutouts. and now this one without the cutouts, but with the reoriented electronics board, as well as a broader array of vanes at the sort of outlets on the backside of this piece of equipment. And let's quickly see if we should. I don't want to fire up the post-processor now again. So I think you know where this is going, right? So simple design changes identified with simulation led to significant gains in terms of peak temperature here, right? So this is sort of bringing it now together. We see on the left the first design we've made. We had a problem with some components. Now on the right, and again, to stress the point, this design isn't more expensive to produce. This design doesn't use more energy to cool the system, right? It has the exact same, essentially outside constraint, but it leads to a more resilient design, a more resilient piece of equipment towards electronic component failure, with like half a day of engineering time spent. That's essentially, now one thing, just to wrap this up, right? Important to say is that since it's not just a conduction analysis, where we do some rough estimation, but it's really, it simulates the air flow, how it goes through, it models the local heat transfer coefficient, it simulates the local heat transfer coefficient between each part and the air above it as a function or depending on local velocity, material combination, etc. So it's a sophisticated type of analysis that allows us to predict these temperatures with very high accuracy. And so we can really gain not just qualitative, as we've seen, but actual quantitative information from such a simulation. And so we can see here the two things we cared about were the basket temperatures, again at the inside towards the enclosure, as well as junction temperature of the coils. And here we see that design change 1, did improve the baskets. Remember, design change 1 was the cutouts at the sheet metal part. So the baskets were fine, but the electronics were still not fine, right? And so then adding the design change 2 with reorienting the board and changing the vanes led to a significant drop in peak temperature on the electronics board as well. Right? And again, all of that in a browser and half a day of engineering work. That's basically my part. Joe, did you sort of want to comment? Otherwise, we'll wrap this up and see if we have time for a few questions.
No, I think this is good. I think that hopefully this is clear. You can see the marriage of SimScale, Onshape, doing these multiple different design studies is just it's a natural fit, right? And it offers some significant productivity enhancements for sure.
Yep.
What I would suggest is that we can cover some questions that people ask. Nobody can. We muted everybody, but please make sure you go into the questions inside the panel on GoToMeeting or GoToWebinar and ask some questions, because I always find this is one of the more valuable parts of our presentations is be able to answer. We can hopefully answer something. I know one question is up there right now about just how do you get started, what do you do? And so I can show you on if you, for Onshape, you go to onshape.com and you simply request a trial, and our product is really structured in several different ways. You can do a standard or the professional product, which is $1,500 per seat or $2,100 per seat per year. And that it's a very simple thing. It takes literally 2 minutes and you're using Onshape. I don't care where you are, what computer, whatever. It's equivalent of, if I'm sorry I keep referring to old systems, but my past life, I would have to go to somebody, request a PO, go through the PO process, maybe get access to a download at some point. I would download this file and install it on my computer and then hope I can get a license file within another day or two. So, we're 5 days down the road before I can even get the software to start running, and it's just not that that's a really important thing, but it just shows how much things have changed, right? And David, you might want to talk about SimScale on the same thing.
Yeah, I guess what's for us, what Joe just said applies to SimScale as well, right? And what we sometimes see is when when folks that are used to CAD or simulation software that's locally installed, right, you're typically looking at, days or weeks to try, right, and you have install problems, and sometimes the VAR, first wants to you to do certain things until you actually get a copy for testing it. And then, or in simulation, if somebody runs a demo simulation for you, right, it is always canned, right, because you cannot sort of see it, you cannot share the full result with you, you don't, it's a large data set, yada, yada, yada. Hence, people are oftentimes very, very surprised to see that on SimScale, you can essentially within a couple of minutes, sign up and use the free community account and test it yourself and, try around. And once you feel comfortable with it, taking the next step, you switch to a professional plan, and all of this with zero install, no hassle. So yeah, the cloud simplifies those things a lot.
Hey, David, there's a question on there about, what types of analysis SimScale covers. Maybe you want to kind of go through the, what different things you can do with it.
Yep. We're thinking of SimScale as a general purpose simulation environment, meaning we're looking at the most, I guess, prevailing problems, dominant problems in all across engineering disciplines, right? Be it industrial equipment, aerospace, automotive. We have a lot of hardware startups as well that do all sorts of interesting things, over even to architects, civil engineers. So we're thinking of it as a general purpose simulation tool. We do sort of most of the functionality these days is really in CFD. Because we saw a lot of demand for that. But we do have a full suite of finite element analysis as well. So, you name it, neostatic, nonlinear analysis, contact mechanics, nonlinear material types, etc. And then lastly, we do also what we've just seen, thermal analysis, from simple conduction only over to what we just looked at, conduction plus convection, as well as including radiation as well.
Cool. Unless someone has more questions, I think we did good because we wanted to keep this less than an hour. And
it's definitely too many questions to go through all of them, and we wanted to keep it short, right?
Yeah, for sure. What I encourage anybody out there is if you haven't already started using our products, start. And there's no reason to not start today. And one thing that we find that is extremely important for our customers is we really, I said it's a request a trial on Onshape. And we do that because we find, we actually will really help you be successful. You can use Onshape just like you use, let's say, SolidWorks, and it works fine that way. But there's a ton of stuff that we do that's better. And kind of guiding you through a project and making sure you're successful is what we're really good at. And so, feel free to contact me or David, and we'll get you started right away.
Thanks a lot for spending time with us today, and hopefully talk soon.
See you, Dave.
Bye-bye.